when we have two algorithms A and algorithm B, that is learning algorithm LA and LB, now which algorithm is better for us? So what is our underlying question? What is an appropriate test for comparing the learning algorithms? How we say that which algorithm is better for us? How can we determine whether an observed difference between the algorithm is statistically significant? Now we have to prove it statistically. Yes, this algorithm is better or the algorithm B is better. So for doing that, what we do, a reasonable way to define on average, now this is important, on average is to consider the relative performance of these two algorithms averaged over all the training set of size n, which is drawn from an underlying instance of the same distribution. So what we are going to do is that we consider all the training set and we try to find the relative performance, how the algorithm A is behaving, how the algorithm B is behaving, right? Like say for example, when you execute algorithm A, so how much is the error, right? If like say for example, if you have got 10 data points, if algorithm A is able to predict or classify 8 out of 10 correctly and algorithm B is able to classify 5 out of 10, then A is performing better, right? Now in that way, now we try to find the relative difference. Now in other words, now what we are trying to see, now we wish to estimate the expected value of difference in their error. So now I can see here, so now the what is the error, that is the we are going to see the expected error. So for learning algorithm A, right, error, that is the true error with respect to the data set D of learning algorithm A minus the true error of learning algorithm B. Now we try to find that particular difference. Now here what, here L of S denotes the hypothesis output by learning method L, right? So we have L of A means what, for first algorithm A, L of B means for first algorithm B. That is the hypothesis you are going to test. Now this particular general algorithm, now this is so the equation what we have seen, you are going to find the difference between the true error for both the learning algorithm A and B over the given sample space. Yes, over the given sample space. Yes, this is what we want to do it. That is the above expression. It describes the X in errors between the training method A and training method B. Now in practice, now what happens actually in practically, now we know that we are having a limited sample data D0. So our sample size is very small in practice, now when we are going to compare two or more algorithms. Now in such cases, now one obvious approach is to estimate the above quantity is, now we try to divide our training set D0 into a training set S0. That is, now see, now this is our data sample set what we are having D0. Now we divide this into two sets. We divide it into, first one is called as S0. S0 is called as the training set. So S0 is called as the training set and a disjoint test set T0. Another subset is called as T0. T0 is the test set and it is disjoint. Disjoint means if some records comes in our training, then obviously the same record should not be in the if there are certain data set in testing set, now the same data point should not be there in the training, right? That is what we call disjoint test set. So what we are doing, so even from last previous classes also we were saying that, so in machine learning, whenever data set is there, we have two subsets. So one is the training set, the other one is testing. So training set we denote it as S0, testing set we call it as T0. Now the training data can be used to train. So now we take this training data set S0, train both the algorithms A and algorithms B, learning algorithm A and learning algorithm B, right? We give this training set data to both the algorithm, and test data can be used to compare the accuracy of two learned algorithm. Then once both the algorithms are been trained, then we use this test data T0 with respect to both the algorithm, and we try to find the true error. We try to find the difference between true error. Now you can see here the error use this the test set T0, right? So we take the training data set S0, right? So S0 is what? S0 is our training data set. So training data set is being used by both the algorithm, learning algorithm A and B, right? So once the training is been completed, then we take the test data set T0 and try to test both the algorithm A and B and find the error, right? True error, the difference between the true error. So now we measure this particular quantity. So now if you try to look into the two differences between the both the above equation, so that is this equation and that is this equation, both are the same equation but there is slight difference. In the previous equations we were considering our entire sample S, right? So this that is the training data set S, which belongs to your entire data sample D0. Now whereas here, now this data set is divided into, so the training set, two disjoint subset, one is training set S0 and the test set T0. So now error, difference of true error of T0 of LA of S0 minus error, that is true error with respect to, similarly with respect to algorithm B. So those are the two differences what you can see. So the test set is being used to approximate the true error, and we are measuring the difference in error for one training set S0, right? Now we are taking a training set S0 rather than finding the difference for your entire sample S. Now here we are considering our entire sample S. Now here we consider only one particular set S0, right? This is what now we try to see differences between both the method. So now if you look at this particular equation just now what we have seen, so in order to improve this estimator, now if you want to improve this, that is error difference between error of the true error of T0 for learning algorithm A when it is trained on S0, similarly for learning algorithm B. Now is to repeatedly partition the data D0. So now what we are trying to do is that we repeatedly partition data D0 into disjoint training and test set and take the mean of the test set error for these different experiment. Now we try to conduct different experiment by partitioning our data D0. So we try to partition data D0. Now this particular procedure is given in the table, right? Now the three steps. Now it's also called as cross validation. In practical, in machine learning, we use this term cross validation, whereas in our book they have not specified this, given this particular term. Now it's also sometimes called as k-fold algorithm or cross validation algorithm. Okay, so now let us try to see how this algorithm is going to work. So what we do is that first step, we partition the available data D0 into k disjoint subset T1, T2, etc. up to Tn of equal size. So whatever the data is available for us, now we divide that, we partition that into k disjoint subset T1 to Tk of equal size, right? Of equal size, where this size is at least 30. So now we see that in practically when you are dividing your data set, now you have to see that this test set minimum, the minimum data point will be 30. At least there should be a 30 data point, right? So now let us say that, let us try to see, understand here. Now say that this is your data point, data sets, right? So you have got around 30 records in your, 300 records in your data set. Now what we do is that we divide this entire data set D0, that is the 300 records, into k disjoint subset CR into K disjoint subset T1, T2, etc. up to Tk. So we are going to divide it into K disjoint subset such that now each subset is, see, when you divide 300 records into K equal to 10 into 10 parts, now each one will be having how many records? So it will be having at least 30 records. So in this way we have divided, right? So first we divide it into T K, T disjoint subset. Next, for I varies from 1 to K. So now we start from, we take each one. So for I varies from 1 to K, use Ti for test set and the remaining data for training set yes. Now let us start with the first one. Now the first set, right, subset, the first subset T1. Now this is taken for testing purpose and all the remaining data, that is T of K minus 1, that means remaining 9 parts, totally we have 10 parts here. First part T1 is taken for testing and the remaining is taken for training, right? Yes. So we use Ti for test data and the remaining data for training set Si, right? So what is this Si now? Si is equal to D0 minus Ti. So total from all your sample data point D0 minus this one, that means remaining 9. Remaining 9 will be considered as your training set. So then, so we take the first algorithm LA of Si, right? So you take your first learning algorithm LA and you train it with this training set Si. So what is Si now? This part. So this entire thing, this entire remaining 9 parts is called as Si, right? Now you give all this data and you train your first algorithm A. So when you train your first algorithm A, so now you are going to get H of A. So we get a hypothesis from this particular A. Similarly, you take that same Si, train the second algorithm, learning algorithm B. You give Si to B. The same Si data, that is training data set, give to second algorithm and you get collect the hypothesis H of B. Now you find delta I. So now you are going to find delta I, so which is nothing but difference. So now difference between error of Ti for H1, right? For H1 is the hypothesis what you got from your first learning algorithm A minus error of Ti. So now we have one testing data T1. Now you use this test data T1 and find the error. What is the error you are going to get with learning algorithm A? Now again test the learning algorithm B with this data set T1 and get its difference, you call it as Di. Right? Now this is the thing what we are doing for when I is equal to 1. So next loop we go for I is equal to 2. Second time what we do is that now we have divided your data into 10 parts, K equal to 10, right? So we first time we took the first one for testing, right? Now second time when the loop continues, when I is equal to 2, you take the second part. Now this will be your testing data T and remaining this part, first one, and the remaining 8 will be your training data, right? So remaining things will be what? Training data. And now the remaining data, training data, again you give it to algorithm A, right? Here in this step you give to algorithm A and execute that, train that algorithm A, then train algorithm B, right? Then find its difference. Clear? So this is second step. Now third iteration, when you take the third part, you take the third subset as your testing and remaining will be your training. So like this you repeat for I is equal to 1 to K. So then what we do, so we get this delta bar. So you are going to get a delta bar. So now what is this delta bar? So this delta bar is equal to, it is the mean. It is the mean. Right? First time you do, second time I equal to 2, I equal to 3, like this if you keep on doing. When you go for I is equal to 10, the last subset will be your test and remaining all top will be your training. right? So then you find this is equal to 1 divided by k, where k is the number of partition what you have done, and summation of all delta I. So you are going to find the mean error. Now this method we call it as the cross validation. This is how in practice we are going to do it. So now the same thing is explained here. So if you first partition the data into k disjoint subset, right? Same thing is explained. So you can go through this particular thing. So now when we look more precisely, now we can view this delta bar as an estimator of the quantity. Which what is this delta bar is going to tell us? It is E means what? Mean. E of difference between your errors when you got with learning algorithm A and learning algorithm B, right? So now where this S represent a random sample of size k minus 1 by k. So k minus 1 by k means what? Now how many partition we have done? Total 10 partition. So k minus 1 means 10 minus 1, right? So 10 minus 1 divided by 10 into D0. So totally how many data sets we are having? So we are having 300. So data set was 300 and we have divided it into 10 partition, right? So this is 10 minus 1 is 9 by 10 into 300. So it around 270. So you will get, so now what will be your random sample size every time? So every time when you are executing, when you are applying this particular method, so out of 300 data points, 270 data points will be for training purpose and remaining 30 data points will be taken for testing purpose, right? This is what we are going to understand from this. So this the approximate n confidence interval, right? So now we try to say that what is our confidence interval. So the approximate n confidence interval for estimating this particular quantity now by using delta bar. So now we are going to use this delta bar to find the approximation. So now we say that this delta bar what we found just right now, that is the mean plus or minus t of n comma k minus 1, t of n comma k minus 1 into s of delta bar, right? So now here this is our equation now when we are going for the n confidence interval. So now here where t of n comma k minus 1, now it is a constant and it is called as degree of freedom. Now it is called as degree of freedom. This is similar to our Zn. So when we are looked into our earlier confidence interval, now we have calculated the Zn. So now this degree of freedom is similar to our Zn, and S of delta bar is an estimate of the standard deviation. Right now, when you have found the delta bar, when you have found this particular delta bar, that is mean. So this delta bar was the mean for us. Now we find the standard deviation. So multiplied here, we say this term, that is S. It is nothing but the standard deviation of our distribution governed by this mean delta bar. Right. So now here this S of, that is the standard deviation, now is defined by this particular equation. So now how do you find the standard deviation? Now this is nothing but square root of 1 divided by k into k minus 1. K is what? How many partition we have done, right? K fold. K into k minus 1 times summation for I is equal to 1 to k of delta I minus delta bar whole square. We know that, we know how we are finding the standard deviation, right? This is the mean and this is for individual sample point. Variance, square root of variance is the standard deviation. The same thing, we are using our standard function from statistics. Standard deviation is square root of, this is the variance, individual data point minus the mean, square of that, right? This is how we find the standard deviation. And here this n confidence interval, so what we told, now it is also just like our Z score value. Similarly, we will be having a confidence interval table, right? Similarly, for n confidence interval table, now we can try to find t. So here we are calling t, right? So here we told the confidence interval is obtained with we said delta bar plus or minus t of n minus k, right? T of n minus k. So we will be having a table called as t table. So now the same way, now just like z score, now here also for each confidence intervals, now we will be having the degree of freedom, right? So now we try to get that particular constant value here. So we can see that as k tends to infinity, that means the number of partitions, you as you make more number of partitions, so then this t of n minus k minus 1, right? Now it approaches z, and so it becomes our z score value. So when you have got more number of partitions, now it tends to, or we tends towards, this value tends towards our the z score value. So how we get here? So we know that, like say for example here k is equal to how many partitions we have done. So we have made 10 partitions, right? So what is the n values, right? The how many samples we are having, so we try to take that much, and 10k is 10, 10 minus 1 is 9. So we'll go to that particular value in our table and we try to pick that value here if you are talking about 90% confidence interval. Just like our z score value, we try to obtain that particular value from the table here. So when we are going for the confidence interval. So now if you look into this procedure, now what we have described just right now, right? So the procedure for comparing the two learning algorithm. Now here, now this procedure we call it as a paired test. So why we call it as a paired test? Because here the hypotheses are evaluated over identical samples. Now we are having the same samples. Now both the algorithm A and algorithm B, learning algorithm A and algorithm B, are tested as well as trained on same sample space. So we are not changing the sample space, right? So we are not going to change the sample space. That is why it is called as the paired test. Now there might be some other comparison or certain other methods also available for us, but this method we call it as a paired test. Now this paired test, typically it produces tighter confidence interval, because any differences is in observed error is, that is whatever we find any differences in our observed error, now these are due to the difference in hypothesis, not on our difference in our data set, because we are using identical data set. Since the data set is same, if you get any errors, observed errors, the errors will be based on your hypothesis, not on the data set. So this type now we call it, that is why we call it as a, we will be having a tighter confidence in talking our test, right? So now this is what the paired t-test what we have discussed. So we have found the delta bar, so plus or minus, so t of n minus n comma k minus 1 into standard deviation. And now how do you find the standard deviation? With this equation, right? So the next topic here, now it gives us a statistical derivation. Already we said that we have to prove by the statistics that now both these equations are correct. It should have certain valid proof. So the next entire topic of the section, now it tries to give us, we try to take each equation and we try to see statistically that whatever the standard deviation we are having now is correct and it obeys with our sample data. Clear? So now let's go through this. So this, and of course with respect to the examination, because it is there, now you need about much about statistical part here. The overall what we can say is that when we are going for comparison of two algorithm, now we can see that so no single procedure for comparing learning methods. Now we don't have any single method or single way in which you can compare one algorithm with another algorithm. So it is present for us. So it is wise to keep in mind that statistical models rarely fit with our training algorithm. So now it is always better that, or we cannot say that okay, you have this particular, like say paired t-test, so you use paired t-test and find the can you say that algorithm A is better or algorithm B is better for us? So it is very difficult in reality, or in practically we don't have any one method through which we can try to compare one or more algorithms. So we have to use other different methods are also available for us in order to compare, and we have to come up with one particular module. So now this is about the comparing the two. In the next video, now we will be trying to look into the another simple concept called as a instance based learning method. So we will be looking into that instant based learning method. There we will see one simple algorithm called as KNN algorithm. Okay.